I'd like to discuss the integration by parts with you now. Let's take a look at our first problem. First of all, up here on the line, I have the basic formula for integration by parts. Your book does a good job of describing where this comes from the derivative of a product. But all I really need for you to know is how to use this formula. So let's take a look at our very first problem. I want to take the integral of x to the times e to the 3x. Now, you'll notice, first of all, that there are two x terms here. I'm very tempted to use the substitution method for when you basically are using the chain rule. But for that to happen, this would have to be the derivative of what's inside. And you'll notice, unfortunately, x is not the derivative of 3x. So when you have two x terms, and one of them is not the derivative of what's inside, you're struck with the integration by parts method that I'm about to show you. Now, what you want to do is assume that one of these two terms, either the x or the e to the 3x, is the u, and the other one is the v prime, or the derivative of v, in other words. In this case, I'm going to pick u to be the x. And I do that because, quite frankly, when I take the derivative of u, or in this case the derivative of x, I get 1. That's the ideal thing we'd like to happen, because you notice I'm still going to have to integrate u prime times v. If I can make one of these x's essentially disappear, that is going to make my job so easy. That's exactly what happens here, so that's exactly what I want to do. I'll call the ux, the derivative of u is 1, and I'll call the other piece, the e to the 3x, I'll make that v prime, or the derivative of v. Now, to find out what v is, I'll have to integrate this. The integral of e to the anything is, frankly, e to the anything. But remember, I am actually going to have to take this, if I were to test this, the derivative of this should be equal to that. But remember what happens? When you have e to the anything and you take the derivative, you of course get e to the anything, but there's a times the derivative of what's inside. I have a times 3 there. I need to get rid of that times 3, which means there must have been a 1/3 out here to begin with to cancel with that, to leave me with the e to the 3 that I wanted. So when I integrate, I essentially divide by the derivative of what's inside. So I divide by that 3 or multiply by the 1/3. That needed to be there in advance, so that when I took the derivative of e to the 3x, it would cancel out the 3. So I now have the value for v. At this point, the hard work is done. I merely substitute these into my formula. The first thing I have in my formula is uv. So in this case, specifically, I substitute x for the u, and for the v, I substitute 1/3 e to the 3x. Now I need minus u prime, or the derivative of u, times v. U prime, remember, was just a 1. That was the thing we wanted to happen, because now when I take u prime times v, 1 times 1/3 e to the 3x, frankly, is just 1/3 e to the 3x. I'll neaten this first part up by bringing my coefficient of 1/3 out in front of my x. And as long as I'm at it, let's go ahead and take that 1/3 and move it off to the side. Whenever I'm integrating, it's easier if I ignore the coefficient. So I'm really just going to take the integral of the e to the 3x part. Well, luckily for you, we just did that 30 seconds ago. Remember up here? The integral of e to the 3x is 1/3 e to the 3x. So down here, where I have the integral of 3x, I merely substitute the 1/3 e to the 3x part. And of course, I bring down the 1/3 that I had in front. Simplifying this a little bit more, I have 1/3 times 1/3 is 1/9 e to the 3x. And I merely copy down my uv term that I already had. And now I've done. I've integrated by parts, and you'll notice that the e to the 3x appears in both parts. Someone made the comment in class that you mean I have to integrate the e to the 3x twice? And yes, That's the beauty of this problem. Remember, at the beginning we had a v prime. You had to integrate that to find out what v was, but you also had to integrate v again. So you can almost think of it as a double integral, if it helps you to think of it that way. Here's our next problem again. At the top of the paper, once again, I have put the formula for the integration by parts. Here's the problem that I want to integrate. X cubed, natural log of x. Once again, you notice that I have two x's, so I'm going to have to use some sort of special technique. I'd love to use that substitution technique, but you remember that this has to be the derivative of what's inside, and x cubed is definitely not the derivative of the natural log of x. Remember, I want to pick the item for u that essentially makes one of these terms go away. Taking the derivative of 3 or x to the third gives me 3x squared. The x doesn't go away. And frankly, taking the derivative of the natural log of x leaves me with 1 over x, and again, it won't really go away. But you will find this to be helpful because at least the natural log part does go away, and that essentially makes it easier. So I'm actually going to pick the natural log of x to be my u part. The natural log, or the derivative of the natural log, leaves me with just 1 over x. And integrating my v prime so that I find out what v is, I will merely take that x to the third, make it 1 more, and then divide by 4, or frankly, just multiply by 1/4. So I now have all the pieces to my puzzle. I started by identifying what u and v prime were, integrated v prime to find v, and took the derivative of u to find u prime. I now once again merely have to substitute these into my formula. So my basic formula again, if we look up above here, was I took u times v. So in this case, that will be the natural log of x times 1/4 times x to the fourth. That's the easy part. I still have to integrate the u prime v part. U prime was 1 over x. The v was 1/4 x to the fourth. Something very nice happens here. Remember, the whole point was to get rid of that natural log, because doing that, look what happens. My x cancels with my x to the fourth and merely leaves me with an x to the third. I'm also going to go ahead and take that 1/4 and set it aside, so that I merely really have to take the integral of my x cubed. Luckily for you, once again, we just did that up above 30 seconds ago. The integral of x cubed is 1/4 x to the fourth. I'll merely substitute that 1/4 x to the fourth in for my integral. I'll bring down the 1/4, and of course I'll copy down the v portion that I had before. Notice I did do a little fixing here, by the way. I did go ahead and move the 1/4 and the x to the fourth to the front to make it clearer. But that's really all I did. There was no simplification or anything else to do there. At this point, I just merely continue to copy that because it's done. I do have a little simplification that needs to be done on the second portion. The 1/4 times 1/4 gives me a 1/16, and I merely copy down my x to the fourth again. And now I have my final answer. Let's take a look at our next example. Once again, I've copied the formula for the integration by parts here at the top of the paper. And let's take a look at the problem that I need to do here. I want to take the integral of 2t squared times e to the 5t. Now, this is by far the most complicated problem that we've done so far. We're going to have to take this pretty slowly, and I want you to pay attention and even rewind if necessary. The first thing that I want to do is take this 2 and just set it out in front. Set it aside, and just worry about integrating this t squared e to the 5t part. Now I have a problem right off the bat. Once again, I have two terms involving t, but you'll notice once again that the t squared is not the derivative of what's inside. So once again, we're going to be stuck with the integration by parts. But we have another problem here as well. If I try to take the derivative of e to the 5x to make one of my terms simpler, easier, and even better if I can get one of the t's to go away, this doesn't help at all because the derivative of e to the 5t is e to the 5t, but then I even have a times 5, the derivative of what's inside. So if I take the derivative, I actually make that more complicated. So that's definitely not what I want to use for my u. Instead, I'm going to pick my u to be the t squared part. Now, admittedly, this will not make it go away, but it will make it simpler. Right now I've got a square. When I take the derivative, I simply have a 2t. The other part I will designate as my v prime. So v prime equals e to the 5t. Now let's integrate it. Remember, of course, that the integral of e to the 5t is again e to the 5t. Checking it again, remember the derivative of e to the 5t is indeed e to the 5t, just like I want it to be. But remember what happens when you take the derivative. We know there'll be a times the derivative of what's inside, times a 5. So I need to divide by 5 or multiply by 1/5. So I need to have a 1/5 out here to begin with, knowing that when I take the derivative then, there'll be a 5 there that will cancel with the 1/5 and leave me with exactly what I want to. Now, I keep doing this as a two-step problem and double-checking the derivative. Those of you in the class that are catching on to how these things work, you may just realize that you really need to divide by the derivative of what's inside. So if you want to say that the integral of e to the 5th is e to the 5th, dividing by the derivative of what's inside and taking that shortcut, I'm really kind of okay with that from this point forward. At any rate, I now have my chart completely filled out. Now I merely need to substitute this into my equation. Remember, the integration by parts, I merely take u times v minus the integral of u prime v. So now I just substitute those pieces in. Remember, of course, that I pulled this 2 off to the side. So I've got to leave that 2 hanging off to the side for the time being. And now let's go ahead and finish this. U was t squared, and my v was 1/5 e to the 5t, minus my integral of my u prime, which was my 2t, times my v, which was my 1/5 e to the 5t. Now I can definitely neaten these up a little bit. First of all, let's go ahead and move this 1/5 out in front to make it the coefficient. Again, I just more or less reordered this first part. My uv, that's all I've really had to do here. This part's going to be a little more complicated. First of all, if I take my 2 times my 1/5, that leaves me with a 2/5. Now, I always like to take that 2/5 and just set it aside. So that's exactly what I'll do here. I'll just set the 2/5 aside. That's going to leave me with a t and an e to the 5t, which I now need to integrate. Now don't forget, I had this 2 out in front. Let's go ahead and just take that 2 through now. I think it's pretty easily done at this point. So 2 times 1/5 would give me 2/5, and 2 times my 2/5 would give me my 4/5. And now you'll notice once again that I need to integrate this t e to the 5t. Once again, I have a problem though. As was the case before, this t is not the derivative of what's inside. I can't use the substitution technique. And you know that I need to use something because once again, I do have 2t terms. So once again, I'm going to be forced into using the integration by parts, but this time I can pick my u to simply be this t, because if I do that, if I pick that u to be t, the derivative of t is just 1. That'll make that just disappear, which is exactly what I wanted. Unfortunately, that still means my v part will have to be dealt with, which is e to the 5p. Now, if my v prime is e to the 5t, luckily for you, remember, we did that before. We already figured out what v prime was. It was 1/5 e to the 5t. I don't really need to work it out again. I can just copy it down. But the explanation again would be the same. It's basically e to the 5t, and let's take that shortcut now, divided by the derivative of what's inside. Dividing by 5, frankly, would just be times 1/5. So now we're ready to substitute this into my integration. First of all, remember that we had this term, this uv from before. Let's go ahead and simply copy that down. Now, let's deal with the integration. First of all, I'm going to take that 4/5 and I'm going to set it off to the side. And remember, when we integrate, it's the u times the v part. So when I integrate this portion, I'll have my u times my v, which gives me this, minus the integral of my u prime v. So I need the integral of my u prime, which is just a 1 now, so that's good, times my v. Well, 1 times 1/5 v to the e5 is just 1/5 e to the e5. Once again, let's go ahead and take this 1/5 off to the side. And now I nearly need to integrate e to the 5t. Well, I've done this 3 times actually now in this problem, so we ought to be getting pretty good at it. The integral of e to the 5t is simply 1/5 e to the 5t. Now let's do some simplification. My 1/5 times my 1/5 would be 1/25. I'd also like to go ahead and move this 1/5 out in front of my t, and that'll simply make this 1/5 t e to the 5t. Now, that's pretty much done, but don't forget that 4/5 that I've had sitting out there from way back up here. You remember, I set that aside before I could even do the integration. So now I've got that 4/5. I'll need to multiply through my solution. So I have 4/5 times 1/5, and actually, it's better to look at this, take the sign with it, like it's negative 4/5 times 1/5, which makes it negative 4/25. And my negative 4/5 times my negative 1/25, which makes that a positive 4/125. And of course, I just merely copy down the algebra in both cases. And now, copying down my very original uv term, I actually have the entire solution for my very original problem. Let's look at one more problem. Again, I've got the formula for the integration by parts here. And when you first look at this problem, you might be asking yourself, why do I even need to worry about integration by parts here? I only have one x. But the truth is, you do need to worry about it. For the simple reason, what is the integral of the natural log of x? I don't know. I know the derivative of the natural log of x, but I don't know the integral of the natural log of x. So once again, I'm going to have to resort to thinking of this as integration by parts. And the way I'm going to get a second term there, frankly, is just to put a 1 in there. So now it's 1 times the natural log of x. And what I've been stressing all along so far is you want to pick u so that it simplifies everything. At first blush, I look at the natural log of x, because we used that on an earlier problem, and I know if I take the derivative of the natural log, that's 1 over x, so I simplified that. If I use 1 as my u, well, that works out great too, because the the derivative of 1 is just 0, and literally everything would go away at that point. That would be great. But the problem is, the other thing you have to remember is, if I pick u to be 1, that means I'm picking the natural log of x to be my v prime. Well, whatever v prime is, I've got to have v, which means I'm going to have to integrate it. I can't integrate natural log of x. That's the whole problem. So there's no way I can make the natural log of x v prime. I've got to make the natural log of x my u value. And my v prime value will then have to be the 1. As I indicated, this isn't that big a deal, because when you take the derivative of the natural log of x, it does simplify it. You have 1 over x now. At least the natural log part is gone. And integrating 1, frankly, is a pretty simple problem. That's just x, correct? Now, substituting in my formula, remember, I have u times v, so that'll simply be my u, my natural log of x, times my v, which is x, minus the integral of my u prime times v. This turned out to be really fortuitous because I have an x in the denominator and x in the numerator, and I merely have to take the integral of 1, which is just x. I did straighten up, you'll notice, the natural log of x times x and merely made that x, natural log of x. So at first blush, what looked perhaps to be the most difficult problem, once you actually see what to do and you work it out, turned out to be the actual, I think, the easiest of the 4 problems I worked for you today.